Hi everyone, welcome back to my channel. So this is the third video in the batch normalization series. In the last two videos we have discussed about the need for batch normalization and then how the batch normalization works in detail. In this video we will discuss about what happens during the backpropagation and also during the inference or testing time how batch normalization works. So we will see these details in this video. Let us have a quick recap of what batch normalization is and how it works. So batch normalization usually happens in the intermediate layers or hidden layers of the neural network. And what we exactly do is normalize or standardize the parameters, whatever the activations coming from the previous layer, and then we will actually shifting and scaling also we will do. Scaling and shifting. This is the input and getting multiplied by weight coming as Z. These are some activations. Now these activations we calculate the mean of them across the mini batch and then you standardize these values, you will get this one. And then you scale that Z by using gamma parameter and then shift it by using beta parameter. These two are network parameters which are learnable parameters. And this is the example calculation. It'll suppose that this is your Z. Okay. Now you calculate the mean of them and then you calculate the standard deviation, variance of course, and you take the standardization for each and every value. So you can see for 3 it will become like this. For 5 it becomes 0.74, 8 becomes 0.29 like this. So all these values are getting shifted to these values here. These values are having mean of 0 and standard deviation of 1. This is what exactly happens in batch normalization. We also saw the significance of gamma and beta. After the standardization, we get this distribution. This distribution is having unit variance and 0 mean. So this is the distribution we get after the standardization. Now this distribution using the gamma and beta parameters, which are learned parameters, learnable parameters of batch normalization, it can actually learn any of these distribution. These parameters actually increases the learning capability of the network. So these are also called as scaling and shifting parameters. So these are learned parameters throughout the training. So that is all about the recap. Now we will do the backpropagation. For backpropagation, we need to see what is the actual computation graph of batch normalization. Here in this example, I am considering two inputs, x1 and x2. So that means that my batch is having two elements and I am calculating the mean from these two elements. So that is why these are connected like this. And after that, I am calculating the variance again using these two variables. At the same time, for variance, we need mu also. So that is where you can see for every calculation, what are the inputs coming, you can observe here. That is the computation graph. And then using these mu, sigma and x1, x2, we can calculate the standardized values of x1 cap and x2 cap. And after that, once we get the standardized values of x1 cap, x2 cap, we use beta and gamma parameters to calculate the final y1 and y2. So these are the equations, and these equations, it is represented in the form of computational graph here. Now using this graph during backpropagation, we need to traverse back. So this is forward pass and this is backward pass. So during backpropagation, we need to traverse back like this. Okay, from y1 and y2 it will come to beta, same way like this, and same way it will go to here. At the same time from x2 and x1 cap it will come to sigma square, and the same time it will come to mu. So for every connection we need to go backwards and see the dependency, and we need to calculate the derivatives based on those dependencies. So let us see how to do that. These are our equations. Now let us consider this is my batch normalization layer and we are giving some xi. So it can be having 10 elements, 20 elements depending on your batch size n. Now this is going as input to my batch normalization layer and I am getting some yi. If you see, these are my yi values. Now if I want to calculate the backpropagation, I already know this loss derivation with respect to yi, because while doing the backpropagation, I might have reached till this part, and then now for the backpropagation of batch normalization, we already know this value. Okay, this is a known value already, and we need to calculate the derivative of the loss function with respect to these parameters. These are 6 values with respect to the standardized x, variance, mean, and the original xi, gamma and beta. Gamma and beta are learnable parameters. Xi and xi cap are actually the inputs, and then sigma square and variance also variables. Whatever variable which is affecting your final value of yi, for everything we need to calculate the derivative to get the backpropagation. So we will use chain rule here of backpropagation. At the same time, we will use summation and product rules also. Those are very simple. And we need to know the basic derivative formulas, like derivative of x square is 2x, derivative of 1 by x is minus 1 by x square, like that. Let us calculate one by one. As you can see, these are the 6 values we need to calculate. And when we are coming from back side, if you observe this graph, we are already reached here. At this point we are. So these values we know. Dou L by dou y1 and dou L by dou y2 we already know. Now from this point, we need to calculate this way. So first we will calculate for beta and then we will calculate for gamma. So this way we are coming back. Now here I am calculating for beta. If I am calculating for beta, I need to do the chain rule because the loss is not directly depending on beta. Loss depends on the y1 and y1 depends on beta. Same way, loss depends on y2, y2 depends on beta. I am doing the addition here because beta is going as input to these two values. So if I want to calculate the loss derivative with respect to beta, it depends on these two elements. So that is why I am doing the summation here. And we know these values with respect to y1 and y2 we already know. Now we need to do with respect to beta. We know this is the equation of y1. Y is equal to, this is the scaling operation of standardized x value, and then this is the shifting operation. So this is the equation we know, and we are doing with respect to beta. So if we are doing with respect to beta, this will become 0 because there is no beta here, so this will become 0. And then finally for beta it will become 1. So this dou y1 by beta is 1. Similarly y2 also it will come to the same equation. Just here it will be x2 instead of x1. It will be x2, and anyway it will get cancelled out, and beta it is 1, like this. And then the total loss value, you just need to add these. So these are only two elements because our batch size is 2 here in this example. If we have number of batch size we don't know, n, then for general equation it is I equal to 1 to n, and instead of y1 y2 we will have a common term yi. This notation I will follow for all of the other parameters also in the derivatives, so you can understand easily. Now we will calculate the derivative of loss with respect to gamma parameter, and the same way gamma is also going as input to y1 and y2 both. So that's why I need to take this summation here. And then these values we already know with respect to y1 and with respect to y2. These are known values. Now with respect to gamma I need to do. And this is the same equation again. Now gamma is in this term and this term is not having any gamma. So this will become 0. And then in this term gamma I am doing the derivative. So x1 is kind of a constant here. So that x1 if I take forward, and for gamma it will be 1. So that is why you got only x1 cap. And similarly for y2 it is x2 cap. And if I substitute this in this equation here, I will get like this. And finally both together as a common term I equal to 1 to n. So 1 to n derivative of loss with respect to yi and xi cap. So if it is 1 here it will be 1 here. If it is 2 here it will be 2 here, like this. The derivative changes accordingly. This is a generic formula for any batch. Now so far we have done the calculation for this. What are the next terms in the graph when you are going back? x1 cap and x2 cap. So we need to calculate the derivatives of these two now. So we will calculate the derivative of loss with respect to x1 cap and derivative of loss with respect to x2 cap. Both are similar looking. So once if we calculate for this one, the expression will be similar for this also. So I am calculating the derivative of loss with respect to x1 here. And loss is not directly depending on x1 cap. So I need to take the chain rule. So this is what the chain rule is. If any parameter is not directly depending on the other parameter here, so we need to go what is the connection between them. So that is how we need to go. So loss depends on y1 and y1 depends on x1 cap. This is the chain rule. And this value we already know. Now we need to do this one. And this is the expression we know. Scaling and shifting operation, right? For this is the expression for y1. Now if I take derivative with respect to x1, this will be gamma. This term will be 0. So that is why you will get this term dou L by dou y1 here, and then for this total term you will get gamma. Similarly for x2 you will get y2 here, that's it. If I write the equation in a generic form xi, then it will be yi. So as I was saying, if it is 1 here it will be 1. For x2 cap it will be x2 cap. If I have 3 elements in the batch then it will be 3 and this will be 3, like this. So it goes on continuously. So here I can be 1 to n. Now we calculate the derivative of x2 cap and x1 cap. So the next term is sigma square. So we will calculate the derivative of loss with respect to variance. If I see carefully here, variance is going as input to two parameters, right? x1 cap and x2 cap. So luckily we already calculated the derivative of x1 cap and x2 cap both. So we can reuse those terms. If I see, loss doesn't directly depending on variance. It depends on x1 cap and x1 cap depends on sigma square. So this, it is going 2 branches, that is why this plus symbol here for both the branches. These terms we know with respect to x1 cap, at the same time with respect to x2 cap, we know these values. Now we need to calculate this one. So these two are similar terms. So once we calculate for x1 cap, the x2 cap value also it will be similar. So I am calculating with respect to x1 cap. If I take this equation, what is the equation of x1 cap? x1 cap is standardization. So standardization is subtracting the original value minus mu divided by square root of variance plus epsilon. This is a constant value anyway. Now I need to do this derivative with respect to sigma square. Sigma square is in the denominator. So numerator is a constant. So I will take this aside. Now this is the equation. It looks like 1 by x. X is actually this one. If it is 1 by x, derivative is minus 1 by x square. So that is what I am doing here. Now in place of x, we have square root of this total term. That is what x is. Now I need to do the derivative of x also again. So I am doing the derivative of x here. Now this looks like a root of x. For root x, the derivative is 1 by 2 root x. That is why I am doing here. Now this minus, I am taking it before. This is the term here. And this square root and square root gets cancelled out and you will get this one. Now for root of x, the derivative is 1 by 2 root x. And then in place of x, we have this total term, sigma square plus epsilon. This is what x is here. I need to take the derivative of x again. So that is what I am doing it here. Now when I take this one with respect to sigma square, I will get 1 and this is anyway 0. So I will get only 1. Out of this total expression, I am getting 1. And this is expression we need. So this is the final expression. Minus 1 by 2 is there. So I am taking it outside here. This is the numerator here. This is the denominator here. And for this is actually 1 by 2. Now we can further simplify this equation. You can see this is the same term and this is the same term. Only powers are different and both are in the multiplication. So you can actually sum the powers. This is here 1 is there and here 1 by 2. So both we can add. So if you see, this is the term here previously we had. Now this is power 1 and this is 1 by 2. Both we can add, and 1 plus 1 by 2 it will become 3 by 2. That is what it will become here. Now if I take this into numerator, it will become minus 3 by 2. So this is your equation now. For x1, this is the one, but I need to do the derivative of loss with respect to sigma square, which is a combination of x1 and x2. So I am substituting this expression here for x1, and the same way the same expression will be there for x2. Only in place of x1 here, it will be x2 like this. So the same expression I am substituting here. Now if I want to take a common term, it will be 1 to n, and then these values we know. So that is a common value now, xi. And then this also common value. Wherever x1, x2 is there, we can replace with xi. Because x1, x2 we have in our example 2 elements in the batch. But if we have like 10 elements in the batch, then n will be 10, right? So this is a general formula for that one. So now we have calculated the derivative of sigma square. Now we need to do the same for mu. So if you see mean, it is going as input for 3 elements here. One is for x1 cap, another one is x2 cap, another one is sigma square. That is why you have 3 terms here. This is the first term, this is the second term, this is the third term. So if you see what I am doing, this is x1 cap, this is x2 cap, this is sigma square. So similarly, we need to take this one. Now this is x1 and x2, both are similar terms. So if you take one of them, the other we can replicate. And sigma square we need to calculate. And whatever these green underlines, these are all known values already. Just now we calculated with respect to sigma square, x2 cap we already know, x1 cap we already know. So if I take this term here, this I am calculating. And with respect to mu I am doing, the expression is same. Because we are doing with respect to x1 cap. x1 cap is actually the standardized value, which is subtraction of mean and divided by standard deviation. Now if you want to do with respect to mu, numerator is the one which is having mu. Denominator, it is not having any mu. So I can take directly denominator in the beginning. And after that, in the numerator, mu is actually in the negative term, so it will be minus 1. So finally, what is this one? For x1 cap with respect to mu, it is minus 1 by this expression. Similarly, for x2 cap also, it is minus 1 by this expression. Because in this particular expression, there is no x1 or x2 variable. So whether it is x1 cap, x2 cap, it doesn't matter. It is the same value we are getting here. So if I take this total expression here with respect to x1, x2, everything, and I substitute this, I will get like this. Okay, dou L by dou x1, and this is a common derivative, and dou L by dou x2, and this is a common derivative. If I take them actually as a generic form, so instead of x1 and x2, I can write xi, and then summation of 1 to n. So in this example, n is equal to 2 for us. That's it. Now what is remaining? We need to calculate this particular value, because this we already know. This we need to calculate. So because mu is actually used in the calculation of sigma square also. So we need to calculate this value. So for this total term, we have wrote the common expression here. Now with respect to mu, I am calculating the derivative of variance. So the variance calculation is this one, x1 minus mu, x2 minus mu. Two values are there. If I have 3, then it will be x3 minus mu, like this. And here this is n. If you see this one, this is actually n. This is not actual 2. N indicates we have 2 elements, that's it. That is why it is 2. Otherwise it should be n elements divided by n. So that is why I wrote in a common expression. So it will be 1 by n, and this is a summation of all of them. So 1 to n elements, and xi instead of x1 and x2, xi minus mu square. So now this term I can take it outside, and this derivative I can directly apply here. So that is what I am doing. I took this expression out, and this is x square. X square derivative is 2x, and then in place of x we have this one. So I am doing the derivative of this. Now if I want to do with respect to mu, I will get minus 1 for this expression, minus 1, and this is a common term. So I can do 1 by n, 1 to n, sigma 1 to n, and this minus I can take forward, minus 2 into xi minus mu. This is with respect to mu, sigma square with respect to mu. Now everything we can put in a single equation. This total term we already know, we got this expression, and now for this one we got this expression. So if you replace this, this one will become this, and after that this is the term here, and then for this term we have this one here. So totally the loss derivative with respect to mu is this expression. So far we have reached till here, mu. We are tracing back and we reach till mu. Now only things remaining are x1 and x2. So we will take x1 and x2. Both are similar, so we will do one of them and we can replicate the other. So if I take derivative of loss with respect to x1, if you check the x1 in computation graph, it is going as input to 3 values. One is mu, standard deviation, and then x1 cap. So that's why in your expression also you will have 3 terms. These are the calculated values in our previous derivations. And this we don't know. With respect to sigma square we don't know, and with respect to mu we don't know. We need to calculate this. x1 cap, and then with respect to x. What is the relation between them? What is the x1 cap equation? This is the equation. This is the standardized x value. So minus mu divided by standard deviation. Now in this x1, where is it? In the numerator. So denominator is a constant. So I can take it side, and then I will take the derivative of the numerator. And as it is I am doing only for x1, it will become 1 here. So this is the expression. So directly final expression is this one. So derivative of x1 cap with respect to x1 is done. So this expression is done. Now I need to do this and then this. So now next we will do with respect to x1 for the sigma square. These are all green, are already known values, and for this we just calculated this. Now for this expression, let us see sigma square with respect to x1. We already saw sigma square expression is this one. Okay, variance calculation. And this one, as I was saying, it is number of elements. In this example we have 2 elements, so that's why it is 2. So but usually it should be n. So that is the reason. So 1 by 2 I am taking it forward. It should be actually 1 by n in the generic form. We are actually taking the derivative with respect to x1. So x2 term, it will become 0 here. And for x1 term, x square derivative will become 2x. And in place of x we have x1 minus mu. If I take the derivative of this, it will be 1. So finally the expression will be 1 by 2 into, it should be 1 by n in generic form. So this 2 is equivalent to n, 2 into x1 minus mu. That is the reason I did not cancel these out. These should not be cancelled out. This particular 2 came from the x square derivative, but this 1 by 2 is actually equivalent to 1 by n here. So that's why this expression should be intact. And if I take the general form, it should be 1 by n, right? So that is why the denominator is n, and 2 into xi minus mu. Fine. If I want to calculate for mu, what is the expression for calculating the mean? For mean calculation, it is x1 plus x2 by 2. So only 2 elements, that's why 2. Otherwise this will be n. Okay. So usually expression will be x3 plus x4, whatever is there, all of them added together by n. That is what the expression should be. So this 2 is an indication that we have only 2 elements. So if I take that with respect to x1, if I calculate, here I will get 1, this will be 0. So the final I will get 1 by 2. In general term it should be 1 by n. Now if I take dou L by dou xi, x1 or x2 as a common expression xi, all of them together, whatever we have calculated so far, this expression, and for this term this is the expression, and for particular this term we have this expression. All of them put together we got this one. So dou L by dou xi cap, and for xi cap this is the derivative we got with respect to xi. And this depends on variance also. This already we know. And variance derivative with respect to xi, it becomes this. Same thing for mean also. So this is the final expression. So we have calculated the derivatives of all of this. If you check, these equations are the exact same things we got from our derivations. So these are the final derivative values with respect to each and every parameter. How the loss is getting affected with respect to each and every parameter, these expressions indicate, okay, how much contribution each parameter is having for the loss. So this is about backpropagation. Now let us see how batch normalization works during testing. Usually batch size is 1 in the testing. During training, for calculating the statistics, we have the batch size, mini batch. It can be some m, it can be 32, it can be 64, it can be 128, powers of 2 usually. But during the testing, the batch size usually is 1. We pass only one element and we get the output. That is how you actually test any model. Gamma and beta are the learnable parameters. There is no issue with them. Okay, we already have these parameters learned during the training and we will use the same parameters. But for calculating the mean and variance, we need a set of elements. If it is only one element, you cannot calculate the mean or variance. That is the reason, how can we do this one during the testing? How this particular expressions work during testing? We need to calculate the mean and variance even during the testing, right? So what can we do? For calculating the mean and variance, one option is to run the entire data set once through the network and then calculate the mean and variance for each and every neuron and then save them in a file. For each and every particular neuron we are having, we need to calculate the mean and variance and then save them here. This particular thing, as we are running in the entire training set at once, we will actually capture the whole training dataset distribution. So this is one option. But is it feasible? Because our training dataset usually it is having hundreds or thousands of dataset elements, right? So all of them you cannot load at a time into your RAM or GPU memory and you cannot do the processing. So this is not a feasible solution because usually you can't load your entire training dataset at once into the RAM. That is the reason you actually split them into batches and then you pass one at a time. So this is not a feasible solution. Then what should we do? What we can do is we can actually keep taking the moving averages and then use those terms during the testing. So while training the model, I can actually calculate the moving average of mean and variance and I can save those values for each and every neuron and use them as a mean and variance for the testing also. That is what usually happens in the batch normalization layer. Usually what we calculate is we calculate the exponential moving average of mean and variance during the training. This gets calculated for every neuron and then these values we will save the last values. Usually moving average will be changing continuously throughout the training. Whatever the final value we got, that we will be saving and those values will be used for testing. Let us see how to calculate those. If you see, this is the moving mean and you have a new mean. Usually when you are having the mini batches, mini batch 1, mini batch 2, mini batch 3 and so on like this, you have n batches, let's say. These are your mini batches. When you have these mini batches, you will calculate the mean and variance for this B1 and this sigma square for this B1 and same way mu you will calculate for B2 and sigma square you will calculate for B2. This is during the training and similarly for B3 and so on like this. For BN also you will calculate mean for nth batch, at the same time sigma square for nth batch. Now what does it mean by moving mean? For the first iteration, for the first batch, this moving mean, so let me represent that by using m. This moving mean is actually equal to mu of B1, that is in the first place. So sigma square moving, same way moving variance is equal to sigma square of batch 1. This is in the first batch. After that, from second batch, it follows this formula. This is a momentum term. This actually gives the weightage of how much weightage we need to give to the moving average so far and how much weightage we want to give for the current batch. This momentum value actually takes that weightage. Usually this is kept as 0.9 in most of the implementations. So for the second batch, what happens? You already have this moving mean and moving variance. This one moving mean you are having and this is a momentum, you have 0.9 plus what is the current batch mean? This is the second batch mean, right? So this is mean for batch 2 into 1 minus 0.9. So it is 0.1. Now this will become my new moving mean. So my new moving mean will be this one. Similarly for variance also. So moving variance into 0.9 plus variance of the current batch, the second batch, because we are doing the second batch now, and 0.1. So this will become the moving average of new variance. So for the third batch, these values are used later in these expressions. So like this, you go till all the n batches, and whatever your final values you got after all the iterations, these values you will be saving. Whatever your final moving mean and variance, these values will be used during the testing. This is how batch normalization works during the testing. If you see here, this is actually the PyTorch documentation of batch normalization. The layer name is batch norm 2D. If you observe, epsilon is used in this particular term. This is just to avoid 1 divided by 0 cases. So epsilon is very small term, default value. And momentum, you can see momentum is 0.1. So the momentum is 0.1 here for calculating the running mean and average. And this is your batch normalization expression total. If you check till here, it is the standardization. This will have 0 mean and unit variance. And after that you have a scaling parameter, and then you have a shifting parameter. Finally you will get a value y. This will be there for each and every neuron. There is a parameter here, track running stats. So this is an optional parameter. It is true by default. If it is true, it will keep on calculating these moving averages. If it is false, then there won't be moving average of mean and standard deviation. It will not calculate these moving average values if I keep this false. So it is an option. If you think like in your model, even during the testing stage, you will have batches of inputs. Instead of a single input, you will have batches of inputs. Then you don't need these moving average calculations, because even though during the testing you have the batches. But in case you don't have batches, or there are chances that you can give with batches and without batches also during the inference, during the testing. So it's always better to keep this true. That's why the default value is true. So when we are implementing batch normalization in PyTorch, when we are using this layer, we don't bother about this parameter. It is always true anyway. We directly pass the features here. These are default parameters. But usually, if this is false, then these values will not be calculated. So this is how the implementation was there in PyTorch. So in the next lecture, we will see the implementation of batch normalization from scratch using only NumPy, not any of the libraries. And we will see for MNIST dataset or some small dataset to see how batch normalization is affecting the training process. So without batch normalization layer, how the training is actually converging, what is the accuracy is reaching to, and with the batch normalization layer, how the training is performing. So that's with the small example we can actually see in the next video. Thank you.